So we've got power series, which is just a polynomial in x. This particular power series is centered at x is equal to 2. And so what we're looking for is an interval around x is 2 through which this thing converges. And converges absolutely. It could converge on the entire number line. It can converge on some combination of open closed interval we're at centered at 2. Or it converges only if x is 2, so that we're adding a bunch of zeros together. Those are the only 3 things that can happen. We find this by setting up the ratio test. We know the ratio test converges if it has a limit L that's smaller than 1. So that's how we start. Breathe a lick through that thing. So we're going to set the k plus first term and divide it by the kth term in absolute value, take the limit, and set it smaller than L, than 1. So set the limit as k goes to infinity. Now let's get the k plus first term. That look like x minus 2 to the k plus 1 divided by the square root of k plus 1 times 5 raised to the k plus 1. Now we're dividing by this, so I put its reciprocal up here, square root of k, 5 to the k, and then x minus 2 to the k, in absolute value, smaller than 1. We're working to solve that for x. We do our usual cancellation with the properties of exponents. That this cancels that one and leaves me x minus 2 to the first. And this cancels that one, leaving me a 5 to the first power. This has nothing to do with k, so I'm going to go ahead and pull it out in absolute value. And we'll have the limit as k goes to infinity. Here's the x minus 2. Then what I have left in there is a square root of k. And then the square root of k plus 1 multiplied by 5. So now you're looking inside that absolute value with the k's, and you're taking the limit as k goes to infinity. And what do you get? 1/5, same power on k, top and bottom. So you take the ratio of the coefficients to give us a 1/5. So I can take the limit away, put a 1/5 here, and now we're solving this for x. When I multiply through by 5, I get the radius of convergence. That's this number. 5 is the radius of convergence, so that means if 2 is in the center and I go 5 units in each direction, I have an interval that on which this series converges. So here's my interval. Here's 2. So 5 units this way. And that puts us at 7. 5 units that way. And it puts us at -3. So far this thing converges for all x between -3 and 7. And we investigate what happens at the 2 endpoints one at a time. So that's what we're going to do next. We're going to check the endpoints. So let's first let x equal -3. Back into the original series. Put a -3 right here. And let's see if we get a convergent or divergent series. So we'll have -3 minus 2 to the k divided by square root of k times 5 to the k. And so that simplifies to a -5 to the k. Square root of k, 5 to the k. And remember that -5 to the k is the same thing as -1 times 5, both to the k. So I can write it like this. -1 to the k, 5 to the k, over square root of k, 5 to the k. That allows us to cancel those 5s. And you tell me what you know about the series that's left. -1 to the k divided by the square root of k. You know anything about that one? It's an alternating p series and it converges. All alternating p series converge. Converges. So that means we include this endpoint. Now we do the same for the other endpoint. Let's let x equal 7. I guess I should have written that down here. Let's say that the absolute value of x minus 2 is smaller than 5 in absolute value. Means x minus 2 is between 5 and -5. It says x is between 7 and -3. Okay, so now we're going to let x equal 7. So I get 7 minus 2 to the k, divided by the square root of k, 5 to the k. So that's a 5 to the k on top, a 5 to the k on the bottom, cancel those. And we have the series that looks like the square root of k, or 1 over the square root of k. And now you tell me, does that series converge or diverge and why? What is it? 1 over the square root of k. It diverges because p is smaller than 1. P is a half here. Diverges because p is a half, and that's smaller than 1. So this endpoint is open, which makes our interval of convergence the interval of convergence is, we said we include the -3 and keep it open on 7. Okay. So let me give you another one. So let's go with the sum from k is equal to 0. Nope, we gotta go from 1 again. 2 times k divided by k raised to the k, x to the k. So this is a power series centered now at x is 0. Now don't be tempted to use the root test because I don't have a k power on my 2 times k. So go ahead and do the ratio test again and let's see what kind of damage we can do with that one. And that's 2 times k, not 2 raised to the k, just 2 times k. Look at it, see if I'm getting in any trouble here. That's your starting point. AK plus 1 divided by AK. It does get tricky pretty quickly. We've got some work to do to do that limit. Here's the limit I'm talking about. We'll be able to cancel the 2. We'll be able to cancel the x to the k. And we'll be able to cancel this k plus 1 with that one. Right? So when we rewrite this, I'm going to have just an x to the first power right here. Cancel that k plus 1. Let me draw a line through it. And so we have what? We have k over k plus 1. All of that's to the k. And I still have this k down there. left? Yes? I put these together because that's the limit that's going to take the work. This limit's easy. Remember how to do this piece? Sorry? That is going to be 1 over E. Any of you recognize that that's 1 over E? We're going to do it. I'm going to break this limit apart into 2 pieces. I'll do this piece. That one, as k goes to infinity, is going to be 0. I'm going to show you this limit again. So first limit, as k goes to infinity, of k plus 1 to the k. That has an indeterminate form of 1 raised to the infinity power. So we use logarithm. Put my limit out there as some unknown number L, and then we're going to take the natural log of both sides. And we did that so that we put the k down there in front. And we write this now as the limit as k goes to infinity of k, natural log of k over k plus 1 is equal to the natural log of L. That's still an indeterminate form. That's the indeterminate form infinity here, and this is the log of 1, which is 0. And so our next step is to take this k and put it underneath the logarithm as a 1 over k. So that it has the right form for L'Hopital's rule. It now has the form of 0 divided by 0. So we take the derivative of the top, divide it by the derivative of the bottom, and see if we can take the limit from there. On top, I have a logarithm. The derivative of the log of u is 1 over u times u prime. So 1 over u gives me k plus 1 over k. And now u prime, I'm going to find by taking the derivative using the quotient rule. So it's the bottom, k plus 1, times the derivative of the top, that's just 1, minus the top, times the derivative of the bottom, which is 1 again, over the bottom squared, k plus 1 all squared. So that's the derivative of the natural log of k over k plus 1. Now I'm going to take the derivative of the 1 over k, and I get a negative 1 over k squared. And that's the natural log of L. So this simplifies to 1 over k plus 1 squared. I'm going to take one of the k plus 1s from here and knock it out there. So now this simplifies to 1 over k plus 1 times 1 over k. Take one of these, one of those. This simplifies to 1. So I have 1 over k times k plus 1. Then dividing by this gives me the reciprocal over here. And now we can take the limit. I've got a k squared downstairs. I have a k squared upstairs. So the limit should be the ratio of the coefficients. Coefficient on top is a 1. The coefficient on the bottom is a -1. So we get -1 out of that limit. And then solve for L to get e to the -1. So when I'm up here, this number gives us e to the -1 as its limit. But this piece here gives us 0. So altogether, that product is 0. All that hard work to get there, we have a 0. Yes, sir.
On the test, we have to show how we get 1 over e, or we can just.
Well, I can probably change it so you might get 1 over e to the 1/2 or something. So if you don't show it and you get it wrong, I can give you no partial credit. If you do show it and get it wrong, I can give you partial credit.
Okay, what if I don't show it and get it right?
Then you're good.
Okay.
The danger warning. Okay, so I have the absolute value of x times 0 is smaller than 1. And you're going to tell me what that means. What does that mean in terms of the radius of convergence and the interval of convergence?
Always true.
It's always true no matter what x is. So the radius of convergence is infinite. The interval of convergence is from -infinity to infinity. Okay, then let me see if you know how to do these two. Find the derivative of the series from k is equal to 0 to infinity, 2 raised to the k factorial, x to the k. So x is the independent variable. Everything else belongs to the counter. It's a quickie. Are you done? For each term, this is a constant. So we're taking the derivative of that, and we get k times x to the k minus 1. Right? So we get, let me just write it out like this, the derivative with respect to x of this thing is equal to term by term differentiation, k x to the k minus 1. But I left this blank. I need you to tell me what the index is on k. Is it still from k is 0 to infinity? starts at 1. When you take the derivative, it changes the counter. And I'll show you that that's true by writing out the first few terms here. If k is 0, 2 to the 0 and 0 factorial are both 1, and so is x to the 0. So I get 1. Then the next term, k is 1, I have 2 over 1 factorial x. Then the next term, when k is 2, I have 2 squared over 2 factorial x squared. Let's do one more term. I have 2 cubed, 3 factorial x cubed, and so on. And so if I looked over there and took the derivative of each of these terms, we put them right here. The derivative of that one is 0. The derivative of this just gives me 2 over 1 factorial. The derivative of this gives me 2 squared over 2 factorial times 2x. The next one is 2 cubed over 3 factorial times 3x squared, and so on. And let's see if that agrees with this. You put a 1 in here, and here, and here, and here, I get this term. Agreed? If I put a 2 here, I get 2 squared over 2 factorial, 2 times x to the first. And then when k is 3, I have 2 cubed over 3 factorial, 3x squared. So remember to change your index when you take a derivative, term by term, through a power series. And you can also integrate term by term in a power series. Okay? Over here. So let's do an antiderivative. Fine. Integral of the sum from k is equal to 2 to infinity, 1 over the natural log of k, x to the 2 times k. So I'm going to do it both ways. I'm going to write out the first few terms, and you can integrate term by term. Then we'll do it in its closed form there. So note that this series looks like 1 over the natural log of 2 times x to the 4th plus 1 over the natural log of 3 times x to the 2 times 3 is 6 plus 1 over the natural log of 4 times x to the 8th. Let's go one more. 1 over the natural log of 2, 3, 4, 5, x to the 10th. That's what that means. And now we're going to integrate with respect to x. It's an indefinite integral, so just to keep you from forgetting your constant of integration, I'm going to put it first. So here's the constant of integration that we get. We'll get one for each term, but then we can add the constants together and get another constant. Now when I integrate this, it's the x that's the variable, that's a constant. So I get x to the 5th over 5, And then the natural log of 2 is down there with the 5. So here I'm going to get x to the 7th over 7, and the 7 is going to be down there with the natural log of 3. Then over here I get 1 over 8, natural log of 4, x to the 9th, plus 11 over 5, x to 11. And then that goes on forever.
On the x to the 9th, is it divided by 9?
Yeah, it is divided by 9. I don't know how that 8 slipped out there. Who put that even number in this problem? Thank you for finding it. Now, if we just did it in closed form over here, we would get this thing to look like the sum. I would have 1 over a natural log of k. Then I get an x to the 2k plus 1. And that 2k plus 1 is down here. And then we get our constant of integration, which I can put right here. Now, my first number down there is a 5 with the natural log of 2. So you can see to get this to be a 5, I keep my counter at k is equal to 1. You only change the counter when you take the derivative. So that's another way to express that bit that we have over there. Integrate term by term. Yes, sir.
You said the counter's k equals 1?
Yes. So that this will give me, oops, 2. 2 is what we started with, right?
Yes, sir.
4 plus 1 is 5. Thank you. And I can't have a natural log of 1 in the denominator. That's why I started it at 2. Okay? So we're going to do a lot of that today. Because we're going to build our own power series. I'm going to take a known one, we're going to build our own. Let me see what you have. One more kind of more of a theoretical type question. Let me see if you understand this power series stuff. So in this example, your decision is that what I say is always true, or maybe false. So my first one is, if my power series from k is equal to 0 to infinity, ak times x to the k converges when x is equal to 4, then it must converge when x is equal to 3. Who wants to take a swing at it?
Maybe false.
Maybe false? What drives you to say that?
Just because it converges on 4 doesn't mean if it converges on 3, the interval could be from 4 to
But where is this power series centered?
0.
It's centered at x is equal to 0. So I know this. It's centered at x is equal to 0, and I know it converges when x is 4. So the radius of convergence is at least 4, which means I could go from here to there. It has to converge then for every number between -4 and 4. It might converge for more, but I know if it converges here, the radius of convergence is at least 4. So this power series is centered at x is equal to 0. To say it converges when x is equal to 4 means the radius of convergence is at least 4. And since 3 is within that radius of convergence, 3 is within that interval generated by that radius of convergence, then the answer is true, always true. So 3 is in here. So this one is always true. Oops. So let's kind of change it a little bit. Let's take the power series, AK, x minus 2 to the k. If that converges when x is equal to 4, must this series converge when, I want true and false, I'll just go state it like that way. Then the series must converge at, say, x is, let's go with -3. So make the picture. Which one, where's this one centered? Where's the center of convergence, center of the power series? X is 2. So x is equal to 2. The radius is at least 4. So that means it has to converge for all numbers between 2 and 6. Go back 4. And so that's -2. So this guarantees that the series converges for all numbers between -2 and 6. It might converge for more, but it guarantees that it converges within there. -3 is just a bit outside, so it could possibly be false. Could be true, but you're not guaranteed it by that statement. Yes?
Why are we making jumps of 4?
Because it converges when x is 4. Oh, sorry, I don't know why we did that. Converges when x is 4, so that means the radius is at least 2. 2, so this goes here. Better, right? So I know it has to converge in here. So that says the radius is at least means this, at least 2. I'm using a capital R for the radius. So -3 is outside this interval. So it may be false. All good? Okay, so let's go and look at the next section, section 8.8. look at things called Taylor series. And Mclaren series. So in this section, we're going to talk about functions that have at least n derivatives on some interval. Not only that, the derivatives are continuous. For such functions, we can find a polynomial that fits f on an interval that contains some number x is equal to c. We can find a polynomial of the form ak x minus c to the k from k is equal to 0 to infinity that fits f on some interval centered at c. So here's what we're looking for. Let me draw in black, say the graph of f. Let's put x is equal to c here, and some function y is equal to f of x here. And if I go out, say, to c plus r and c minus r, I'm looking for some red polynomial that matches that function in that interval, but then it might do wacky things out here. This is going to be polynomial. Let's call it T n, so that it matches the graph of the function on that interval. And I can show you what it looks like by brute force. We need a couple of things to happen. We need them to have the same value, y value, at x is equal to c. We need them to have the same slope at x is equal to c. We need them to have the same concavity at x is equal to c. We need to have the same rate of change in the concavity at x is equal to c. We need all of the derivatives of that red graph to match all of the derivatives of my function f of x at x is equal to c. So that's what we're going to do. I'm going to write it out. I'm going to say, well, okay, we're going to find this polynomial so that f of x, I'm going to write that out. Start k is 0 is a0, x minus c to the 0, plus a1, x minus c to the 1, plus a2, x minus c squared, plus a3, x minus c cubed, plus a4, x minus c to the 4th, and so on. So we want them to match y values at this point. So if I put c in for x here, and c in for every x over here, that tells me that this number has to be f of c. So note that f at c is that constant there. We want them to match. Now I'm going to take the derivative. The derivative of this thing here, well, that's a constant, so its derivative is 0. The derivative of this x is 1, so I get a1. The derivative of this is 2 times a2 times x minus c to the first power. The derivative here is 3 times a3 x minus c squared. And then 4 times a4 x minus c cubed, and so on. Now to make them have the same slope at x is equal to c, then I need f prime at c. Well, if I put a c in here, all those terms are 0, so this number has to be f prime at c. Now I'm going to take a second derivative. I'm going to take a derivative here. This constant term has a derivative of 0. That has a derivative of 1, so it leaves me 2 times a2. This becomes 6 times a3 times x minus c to the first power. This becomes 12 times a4 x minus c squared, and so on. Now I want the derivative at x is equal to c to match the derivative over there at x is equal to c. So that says that f double prime at c is equal to 2 times a2. So a2 is f double prime at c divided by 2. Let's do one more derivative. So one more derivative for f triple prime. At any x, the derivative of that will be 0. The derivative here just leaves me 6a3. The derivative of that gives me 24a4 times x minus c to the first. And then I have higher order terms. But when x is replaced by c, I just get 6a3. All of these others will have an x minus c on there. So when x is c, they're all 0. So that says that a3 is the third derivative of c divided by 6. If we continue on this way, what would you think a4 would be? What's the fourth term here going to be? By looking at what the next derivative gives you. The fourth derivative of f evaluated at c over 24. Well, look at the pattern of numbers. I've got essentially a 1 here, a 2 there. 6 can be thought of as 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. These are all going to be the factorials of whatever integer the power of the derivative is. So I can think of this, a3 is the third derivative at c divided by 3 factorial. a4 is the fourth derivative at c divided by 4 factorial. That's going to happen all the way down the line. The coefficients here are going to be the order of the derivative of f evaluated at x is c divided by that number factorial. And when we rewrite that now, we have a Taylor series for our function f. it looks like this. So we can write that f of x is equal to f of c plus f prime at c divided by 1 factorial times x minus c to the first power plus f double prime at c over 2 factorial times x minus c squared plus the third derivative of f at c over 3 factorial times x minus c cubed. Let's put one more here. The fourth derivative of f at c times x minus c to the fourth over 4 factorial. And that's how we build the infinite polynomial that converges to f on an interval containing x is equal to c. We can write it out in summation form. Let's go from k is equal to 0 to infinity, where I have the kth derivative of f, so that the 0 derivative of f means f itself, evaluated at x is equal to c, divided by k factorial, and a reminder that 0 factorial is equal to 1. And then we have x minus c to the kth power. And this is called the Taylor polynomial, or the Taylor series for f of x centered, let's just say at x is equal to c. And this means that if a function has a Taylor series, it has only one Taylor series. It is unique for the function, and it's easy enough to make. Take a bunch of derivatives, evaluate it at x is equal to c, use those divided by the factorials in front of x minus c to the power. If we take c to be 0, then this Taylor series is called a Mclaren series, which is kind of slimy that somebody else put their name on this guy's theorem just by taking a particular value of c. So the Mclaren series says that f of x can be written as f of 0 plus f prime at 0 times x over 1 factorial plus f double prime at 0 times x squared over 2 factorial, and so on. In summation notation, it's the sum from k is equal to 0 to infinity. The kth ordered derivative of f evaluated at 0 over k factorial times x to the k. So let's look at finding a Taylor series. For f of x is equal to the natural log of x. Now I can't do a Mclaren series because the natural log of 0 is not defined. So let's shift it over to x is equal to 1. Let's find the Taylor series for f of x is equal to the natural log of x centered at c is equal to 1. So we're just going to follow the recipe. Step 1, take a boatload of derivatives of the natural log of x. Step 2, evaluate each derivative at x is equal to 1. Step 3, fill it in the formula. So let's start taking a bunch of derivatives of the natural log of x until I run out of room here. So I'm going to start with f of x is the natural log of x. F prime of x is 1 over x. The second derivative is negative 1 over x squared. Third derivative, think of that as x to the negative 2. So it'll be 2 over x cubed. The fourth derivative, think that as x to the negative 3, so it's going to be a negative 6 over x to the 4th. The fifth derivative, that's a negative 4, so it gives me a 24 over x to the 5th. I think I might have room for one more. So 5 times 24, that's going to be 120, and be negative over x to the 6th. I only went to 6 just because I had room for it. So take 6 derivatives of the natural log of x. Now we're going to put 1 in for each x. As I said, we're going to center this at x is 1. So the natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is a negative 1. 2 over 1 cubed is 2. Negative 6 over 1 to the 4th is negative 6. 24 over 1 to the 5th is 24. And then finally, the 6th derivative at 1 is just the negative 120. Now I'm going to remind you of the formula, and we'll fill it in. I'm just going to copy this formula down again. Formula for Taylor series says that f of x is f of c plus f prime at c over 1 factorial times x to the 1, x minus c to the 1, plus f double prime at c over 2 factorial, x minus c squared, plus third derivative at c over 3 factorial, x minus c cubed, blah, 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 blah. So I'm just recopying that formula from over there. And I'm going to use my numbers. My function is the natural log of x. F of c was 0. F prime of C was 1. And C is 1. F double prime at C is negative 1. F triple prime at C was positive 2. Let's go ahead and use all my terms. See how far this person here can see it on my board. I can go all the way to the end of the board, so here we go. So let's see, I'm on the third derivative. I used that one, that one, that one, that one, so we're here. The fourth derivative was negative 6 x minus 1 to the fourth over 4 factorial. Then we have 24 x minus 1 to the fifth over 5 factorial. And then we have negative 120 x minus 1 to the sixth over 6 factorial, dot, dot, dot. So we have an alternating series. I'm going to try to write this in closed form. I want to see if I can get a pattern here so that I can put it in this form. And I recognize something about the numbers 1, 2, 6, 24, 120. Those form a pattern. 1, 2, 6, 24, 120. Those are the factorials. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial, and 5 factorial. And so this one would be 0 factorial.
Why can't the second one just be 1 over like the first one?
Because I want to make a pattern starting at, I want to make my pattern to start with my 0 factorial so that I can continue my step. I don't want to have 2 1 factorials in a row.
Like the alpha B?
Sure, but it's not going to help me write the general formula if I do that. I wanted these to increase by 1. I'm looking for a pattern so I can write the general formula. So look over here. I've got a 1 factorial divided by 2 factorial. 2 factorial divided by 3 factorial. 3 factorial divided by 4 factorial. These will all cancel, won't they? So I can cancel here and knock off the factorial. This is 2 factorial, cancel into 3 factorial, and it knocks off the factorial. 3 factorial divided by 4 factorial knocks off the factorial, just leaves me 4. All the way down the line, that's 4 factorial, and that's 5 factorial. So here's what I've got so far. Let's leave off the 0 term. I've got 1 times x minus 1 plus, minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the fourth plus 1/5 x minus 1 to the fifth minus 1/6 x minus 1 to the sixth. So let's put it in general terms. And I'm going to start at, if I leave the 0 here, I can start at 0, but I don't want to. I'm going to start at k as 1 and go to infinity. So how can you describe for me what happens to the x minus 1s? All right, first step, notice that it alternates. Positive, negative, positive, negative. So I'm going to stick a minus 1 in here. K is my counter, so I got to increase K by 1 so that my first term is positive. That means when K is 2, I've got an odd power, so I'm going to get a negative sign, and so on. That'll guarantee that the signs alternate. Now notice that the number in the denominator is the same as the power on the x minus 1. So my next term is going to show that. I'm going to have x minus 1 to the k. And then I want the number in the denominator to match that. Do you think that what I've written there describes the line above it? Yes, no, maybe. You think that's the general formula then? What I want you to do next is find the interval of convergence. What size interval around x is equal to 1 will this converge to the graph of y is equal to the natural log of x? Okay, so now find the interval of convergence. We're going to do that ratio test. Do that ratio test right there. Take the limit. K goes to infinity. So I'm going to have minus 1 to the k plus 1 plus 1. That gives me a minus 1 to the k plus 2. Then I'm going to have x minus 1 to the k plus 1, all divided by k plus 1. Then I multiply that by minus 1 to the k plus 1. And x minus 1, so it's not k, yep, x minus 1 to the k. And then up here, k. We're trying to find out what makes that smaller than 1. So what cancels?
The negative one's still, right?
The negative 1's gone because I can get rid of the negative 1 to the k. Then I've got a negative 1 squared, which is 1. Divided by negative 1 is negative 1, but it's an absolute value, so that's 1. So I don't even have the 1's anymore. I get an x minus 1 to the first power on top, and then k over k plus 1. You with me to there? So the limit of the stuff involving the k is what? Just 1. So now we solve x minus 1 is smaller than 1, which means x minus 1 is between 1 and negative 1. So x is between 2 and 0. So my radius of convergence was only 1. 1 unit on each side of my center, and x is equal to 1. Now, there's no way this is going to converge at x is 0, because remember, this represents the natural log of x, and this doesn't even exist at x is 0. So the power series won't either. But if you plug that in here, you'll see that that's true. So let's do that step formally. So now I'm going to check the endpoints. X is equal to 0 makes my series look like -1 to the k plus 1 over k. And then when x is 0, I get another -1 to the k. All right, so when I multiply like bases, I add exponents. I think something went wrong. What did I do wrong? Let's see. A is 1. First term is positive. A is 2. It's negative. Well, I wanted that thing to be even up there. But it's odd. Can't possibly converge at x to 0, but this is telling me it does. Arg. What did I do wrong? I can't have it converge at x to 0. Power series for the logarithm. That was a k minus 1. Let's do that. Rats, rats, rats. I have to figure it out.
You might have to discover something including you.
The natural log of 0 is not defined, so I can't have this converging. I'm sorry?
You started at k equals 1 and k equals 0, so you don't actually have ln of x.
What do you mean? K has nothing to do with the x. Right? That's moving the x. I started it at 1 so that my first power would be an even number so that I get a positive 1 here. That's why I started at 1. And then the next one was going to be negative. So when k is 2, I got an odd power, and so it's negative. So this is only supposed to converge on the open interval from 0 to 2. And I got it converging on the closed interval, and it can't. So I did something wrong. So let me look back here. X is 0. It's -1 to the k. So it's -1 to the 2k. But then there's the +1 that makes that son of a biscuit odd. Arg. Same deal is going to happen when k is 2. Well, let's just pretend we didn't do this last part, because I didn't get it to work, and I don't know why. Because it can't converge at x is 0. I need to look that up. I need to see what went wrong with my naming over here. It's going to converge for 0 and 2 according to the formula that I've written, and that's not good. It's only going to converge on the open interval, where x minus 1 is smaller than 2. And what I wanted to do next was get you the, well, I'll do that next time, I suppose. I'll figure it out. I'll figure out what went wrong here. It has something to do with my naming. But it's going to converge only on the open interval. And we're going to develop some Mclaren series for some basic functions. So maybe you might want to try these. Write out the Taylor series centered at x is equal to 0, for e to the x, sine of x, cosine of x, and the inverse tangent of x. And that's where we'll start on Thursday. Okay?
Is that what our calculator does? And you put in that for
What do you mean?
like, we put in ln of 10, does it do all that stuff where x is 10?
Oh, I don't know. I don't know how the calculators are programmed. They can.
It's possible.
It's possible. All right, everybody good at home? Everybody's gone at home.